All right, we are now recording. Let me get the slideshow set up from current slide, if it'll get there. There it is. And before we get going on the pre-calculus algebra, let me hit these couple more announcements. And I think for this class, I may have told you bad information last time because I had gotten bad information or else it changed or something. But next week, office hours this week are as normal, okay? Next week, however, since Michelle's here, we are going to change a few things, okay? Not changing, it's just a bad set of circumstances. First, I have a doctor's appointment next Tuesday. That's the bad news. The good news, it doesn't affect this class any, all right. We'll still meet as normal next Tuesday. However, as soon as class is over, I'm out of here. Okay, so my poor trig class, they miss it. Okay, but, well, wait, I'll take that back. Office hours this week are not normal. Okay, because the trig class Tuesday, when I met with them and went over the stuff, I explained to them that we would be missing and I wanted to make it up. The time at least one person could come was tomorrow at 11 o'clock, okay? So I will be making up my trig class tomorrow, 11 to 12:15, the one that I'm going to miss next Tuesday. So that means my office hours are changed in possibly two ways, okay? And I don't know this yet because I was going to check with my boss yesterday, but we weren't here yesterday, and he probably isn't here yet this morning, so I couldn't check with him when I got in this morning. So here's the deal. I'm going to be on this campus. Normally on Fridays I'm on Birmingham campus, 7:45 to 1 o'clock. This Friday I know I'll be here from 11 to 12:15, and since I'll be here till 12:15, I'll stay here till 1 o'clock. So my office hours from 12:15 to 1 will be here on this campus. What I don't know is whether I need to go to the Birmingham campus or not. If I do need to, then I'll be going there first, taking care of whatever is happening then, and then coming here before 11. And one thing is happening, I think. We are required to have a departmental meeting, we found out Tuesday, before the end of this week. And since we didn't have class yesterday, and I hadn't heard back from enough people to schedule it, well, today, almost impossible. I only have a window between 10:45 and 1:15. And I don't think other people would be able to meet then. The ones I had heard from couldn't. So we're going to have a departmental meeting. My guess is going to be on the Birmingham campus. So I'm guessing I'll be on Birmingham campus from 8 till about 10:30. But somewhere in there, we have a departmental meeting. I am guessing probably about 9 o'clock. Okay? I don't know that for sure, but I believe that's going to be when it's going to. I haven't seen all the emails, so responses to it. But right now, that's what I'm guessing. So tomorrow morning, 7:45 to 9, probably, I have office hours on the Birmingham campus. Probably be out of the pocket from 9 to 10, and then back in the office maybe from 10 to 10:30. But at 10:30, I have to leave to come over here to be here at 11 o'clock.
Okay.
Yeah.
So next Thursday, are we still going to have class or not?
Okay, no, I don't think we can. You're not going to be here at 8, can you?
I don't know. I didn't hear anything.
You haven't heard anything about it yet, okay. Well, then I guess I haven't heard anything either. I haven't seen the emails, so I assumed they had come up with some. But the thing starts at 9 on the Birmingham campus, okay? That means I've got to leave here by 8:30, and I think I probably need to leave a little earlier than that. So to meet for 15 minutes, I don't think makes a lot of sense. And I imagine you have to be there, like you said, an hour early. So if you have to be there at 8, no way you could be it. So that was going to be the next thing I talked about. No, the next thing. All right. So this Friday, office hours, Birmingham campus, like tomorrow. Birmingham campus, 7:45 to 9, I'm guessing. And then maybe from 10 to 10:30. And then from 12:15 to 1 on this campus, okay? So really broken up office hours tomorrow. Then on Tuesday, I have my doctor's appointment. This class meets as normal, okay? But at as soon as this class is over, I'm heading to Birmingham to for my office visit, and since it goes, the labs are at 10, the appointments at 11, and hopefully I'll be through by 12. Hopefully before 12. So I should be back in the office by 12:45 if I have class at 1:15. So I will have a few office hours, but not many, about 12:45 to 1:15 on Tuesday. Then on Thursday of next week, we have Honors and Awards Day on the Birmingham campus at 9 o'clock, which I know, I'm guessing Amber will be gone. I don't know if any of the rest of you are getting an award, but if you are, you probably have to be over there. And if not, I know I have to be over there, and I'm guessing I have to be there by at no later than 9:45. I haven't seen, like Amber has an email on it yet. So if I have to be there by 8:45, I'd have to leave here by 8:15, and that doesn't make a lot of sense to have a class for 15 minutes. So we probably won't have class on Thursday of next week, okay? Now, that's a school-related thing, so I don't feel as obligated to make that up as I do for my trig class, because that was my doctor's appointment. I had nothing, couldn't do anything about it, but I did try to, we are making that one up. Do you want me to record a class to make up the one we're missing next Thursday? Oh, but Michelle is so kind. I can't believe it. Okay. So anyway, we'll be here Tuesday, but not Thursday. I'll go straight to the Birmingham campus. All right. Enough announcements, aren't they? And did I say, I didn't even finish. The next Friday, I won't be on Birmingham campus at all, or on this campus at all. I have an infusion that's scheduled for 8 o'clock. I have to be there by 7:45, and it lasts all day. So I won't be there next Friday, either campus. This campus, there from 7:45 until 9, and a meeting from 9 to 10, there from 10 to 10:30, on the road from 10:30 to 11, here in class from 11 to 12:15, and then here office hours from 12:15 to 1 o'clock. All right, that's tomorrow. Any questions before we get going on today? All right, what we left off with last time is, I know it's so long ago and you've been on holiday for a day and that kind of stuff. What we've been doing, this chapter is polynomial and rational functions. This is the last section on polynomial functions, even though we deal with them in the next section too. But next section we're doing rational functions, which are ratios of polynomials. So still doing polynomials. But what we were doing was basically finding zeros of polynomials and factors of polynomials. Okay? Now, we know by the fundamental theorem of algebra, Gauss's theorem, that there's at least one zero for every polynomial function. And even more than that, there's one for every degree of the power. For instance, if this is your polynomial function, this has n zeros, n factors. But those could be complex. Okay? You can have up to n real zeros. So what we've been doing since then is trying to find out how to determine those zeros. Now, if you can factor it, by all means. But usually those are limited to quadratic and maybe a few cubic functions or a few that you might be able to factor by grouping. But basically, factoring runs out for big, long polynomials. They're really hard to factor. So what we're doing now is trying to determine clues. Now, we already have one. If all these coefficients are real numbers, are integers, all the coefficients are integers, then we can use the rational zero test. Okay? And there we can find some possibilities to use as zeros. Okay? You use synthetic division and see some others too, and here's one. The following theorem, called Descartes' rule of sign. By the way, Descartes. Anyone know why they named it Descartes' rule of signs? He was a very famous mathematician, but not just mathematician, philosopher. Have you ever heard the quote, "I think, therefore I am"? René Descartes. Great mathematician, but also a fantastic philosopher as well. He came up with this rule of signs. It sheds more light on the number of real zeros of a polynomial. So this, used in conjunction with the rational zeros test, you can eliminate a lot. Remember, sometimes those had strings of possible zeros. Well, Descartes' rule of signs lets you know that you can limit the number that you look at. So here's what his rule of sign says. If f of x is a standard polynomial, a sub n, x raised to the nth power, a sub n minus 1 times x to the n minus 1 power, plus dot, dot, dot. You know, as you count down on the degrees of your x's, you finally get down to a sub 2, x squared, plus a sub 1, x, plus a sub 0, times x sub 0, which is 1. So don't write that. Let that be a polynomial. Now we have real coefficients. Okay, not just integral coefficients. You can have fractional coefficients. You could have decimal coefficients. You could even have irrational coefficients. Perfectly fine. E, pi, square root of 2. Those could be your coefficients. As long as you have real coefficients, no complex coefficients with imaginary parts, and this a sub 0 is not 0. I already know a sub n can't be 0, otherwise it's not degree n. Now a sub 0 can't be 0 either. Then the number of positive real zeros of this function f, the number of those, is either equal to the number of variations in signs. That's why it's called the rule of signs. So what you do, you look at these coefficients. If this is a plus and a plus and a plus, then you have a minus and a minus and then a plus and a plus and a plus, how many variations in sign do you have? Well, these pluses are no variation. But then if you have a minus here, there's one variation, but another minus, that's not. But then with minus the plus, that's another. So you'd have 2. So you could have up to 2 positive real zeros for that polynomial. Or less than that number by an even integer. What's only even integer less than 2? 0. So that means you have either 2 or 0 positive real zeros. So what does that mean? If you're using the rational zeros test and you find one positive real zero, keep looking because there's got to be at least another. Okay? Keep looking. Now that's the first part of it. The number of negative real zeros of f is either equal to the number of variations in sign of f of minus x, a different function. Put a minus x here, and what's that going to do? If this n is even, that doesn't change the sign of that. But if the n is odd, that does change the sign of that. If that was a plus, it becomes a minus. If the next one is even, then it doesn't change the sign, whatever. If f of minus x here would not change that sign, because minus x squared is the x squared. So that sign wouldn't change. But a minus x here would change that sign. And nothing would change that sign because you're not multiplying by negative x. So you rewrite the function as f of minus x, and then you have the number of variations in signs there. Give me a number. Make up a number. 2 again. We've already done 2. Bigger number. 8. Oh, we found 8 variations in signs of f of minus x. So that's a big polynomial. How many negative, f of minus x. How many negative real zeros could we have? 8 or 6 or 4 or 2 or 0. Okay. That was going to take a bit of work then. Start going, and if when you're doing your rational zeros test, you wind up with 1, keep going. You know you're going to have at least 2. Okay? If you get a third one, then keep going because you're going to have at least 3. I mean, at least 4. You know, you just keep going. When you run out, then you stop. There's some other rules too, so don't worry. The variation in sign means that 2 consecutive coefficients have opposite signs. Okay. And PowerPoint isn't advancing. Why isn't it advancing? There we go. When using Descartes' rule of signs, a 0 of multiplicity k should be counted as k0. So remember when we were doing our rational zeros test, if you found x equal 1 was a 0, try it again, you know, because you got to see if it has a multiplicity. So every time you find 1, if you found up to k, that would be k zeros. Give me a number for k. 3, okay? If k was 3, and you found those 3 k's, and you had an even number of zeros you're looking for, you know you got at least 1 more. If you only had an odd number, keep going, and if you don't find any more, it could be, those are the only 3 that you would have positive or negative real zeros. Okay. For instance, here's a polynomial. How many variations of sign does it have? Say again? 2. It's plus, minus, there's 1, minus, plus, there's 2. So that has 2 variations in sign. So what does that mean? Right. So that would have how many? Either 2 or 0 positive real zeros. Those are positive real zeros. How would you determine if it has any negative real zeros? Say again? Okay, you put an f of negative x. So that would become negative. What would this become? Positive. What would that become? That doesn't have an x in it. So it stays plus 2. So then you'd have a negative, positive, positive. How many variations in sign? Negative, positive, positive. 1. So when you're looking for your negative, if you find 1, quit looking. Even if you have a whole string of plus or minus, plus or minus, plus or minus, you found 1 negative, stop. That's the only one that's there. Okay, so you eliminate all those others that you were looking for. Okay, well, let's see what happens here. They did it for you. Shame on them. And by the way, they had multiplicity of 1 here. What would have been the 0 for this one? X equal 1. X equal 1. And guess what? There's 2 positive, 1 negative. Yes, the Descartes rule of sign works. You can see the 2 positive real zeros, x equal 1, or its brother, x equal 1. Okay. The other. Multiplicity of 2. Count those as 1. And guess what? When you started doing that, and this would have been so easy to do, because 1 is so easy to do, you just look at the coefficients. 1 minus 3 plus 2, that adds a 0. So you know x equal 1 is a 0. So you do your synthetic division. 1 into 1, 0, negative 3, 2, because you have to account for that missing term here. And then do your synthetic division once. And you're going to get a quadratic at the end, factor that, and you get the result. So, Descartes' rule of signs, you wouldn't even need in this case. But it's good to know when you do get your answer, yes, it fits Descartes' rule of sign. Make sense? It does since Terrell's here. Okay. Has anyone else come in since I called off? I didn't mark. All right, let's do example 9. There is our polynomial function. It says here just determine the possible numbers of positive and negative real zeros. Not rational zeros, but real zeros for this polynomial. Anyone give me a positive? Up to 3 positive zeros. How did you get that? 3 variations in sign. What were they? Plus to minus, minus to plus, plus to minus. 3 variations in signs. Or what? Subtract 2 from 3. 1. So you know you have at least one positive real zero. So look until you find it, okay? You got to have at least one. Okay, because you count the variations in sign. 1, 2, 3 variations in sign. That means you either have 3 zeros or subtract 2 from it is 1. That's the Cart's rule of sign says, okay?
So it doesn't have to be even, it just has to have an even gap between them.
Yeah, an even gap between them, exactly. Notice what it says. The number of positive real zeros is equal to the number of variations in sign, in our case 3, or less than that number by an even integer. 3 or 1, you can't subtract. You can't have a negative 1. Okay, so you stop that. So that had 3 or 1. Okay? Make sense? Okay. Now, so we have 3 or 1 positive real zero. Okay. Now, since this polynomial has integral coefficients, we expect those to be rational zeros too. They may not be. You may have an irrational zero, but we at least hope they be rational. Okay, at least one of them. If one of them is rational, then the other 2 could be irrational, plus or minus, square root of something. Okay. How about number of negative real zeros? That gave us positive real zeros. Took care of that one. How about negative real zeros? What do we consider? F of negative x. And what would f of negative x be? Negative 3x cubed. That's an even exponent. If you put a negative x in here and square it, you get a positive x squared. So that doesn't change the sign. Put a negative x in here, and that becomes a negative x cubed, so you do change that sign. So the odd exponents change the sign, the even exponents leave the sign alone. So that would be minus 5x squared at minus 6x. You're leading me astray here. Okay. Minus 6x minus 4. That's an even exponent, 0. Okay. How many negative real zeros do you have? None, because you have no variations in sign there. So therefore, when you have your rational zeros test, don't try any of those negatives. You know you don't have any. So you see, you've eliminated half of your possibilities there. The Cart's rule of sign give you another tool in your tool belt to keep you moving faster and more efficiently. Does that make sense? That's all they're asking for. They're not saying find them. They just said, what would be the possibilities? This would be 0 negative, get out of there, real zeros. Okay? 0 negative real zeros. Now, that's all they ask for. Do they actually find them? No, I don't think they do. Okay. Say again? I would use synthetic division. I'd use the rational zeros test and synthetic division. Okay. Of course, the first one would be, let's just try to see if 1. That's always a possibility, right? Then you just look at your coefficients. 3 minus 5 is negative 2. Or it's 0. Ding, 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 ding. You found a 0. a positive real zero, so you know you've got your 1, because that's 3 or 1. You know you've got the 1. Keep going, use synthetic division, and you try 1 again. Now, I'm not working it out, but try 1 again. If 1 works, you found the second, you know you got a third one. Keep going, but then don't try any of those minuses. In fact, don't even write the minuses. You don't need to do plus or minus, just do the pluses, okay? And what would be the rational zeros? What would be your possibilities for the numerator? Again, factors of 4. 1, 2, and 4, and your denominator? 1 and 3. You don't have to do plus or minus now because you know there's no negative real zeros. So just do the pluses. So you've eliminated half of them right there. Thank you, Descartes. You saved us some time. So that determined it. And it shows a graph too. Well, let's only clear what I've done and let's see what they do. Original polynomial has 1, 2, 3 variations in sign. Okay? They do 1, 2, 3. I don't know why, but fine. 3 variations in sign. That gives you 3 or 1 positive real zeros. Okay? Now, then you do the f of minus x, just like y'all did, except you did it faster. They write it out. Maybe it's a good idea to write it out. Put that negative x in there and cube it, square it, and raise it to the first power. The first one will give you a negative 3x cubed. The next one keeps it a minus 5x squared because a negative x cubed is a negative x cubed, so that changes that sign. A negative x squared is a positive x squared, so that doesn't change that sign. Negative x does change this sign, and of course there is no x, and that sign stays the same. So the negatives have no variations in sign. That means you have no negative real zeros. None. So from Descartes' rule of signs, the polynomial has either 3 positive real zeros or 1 positive real zero and definitely no negative real zeros. So you find the 1, well, they drew a graph. That did it for them. And by the way, didn't you know you had a 0 anyway? Just the function. Why? Odd power. So this is odd degree. That means it's either going to be like this or like that. Remember your end behavior? Still comes in. Polynomial functions are 2 things: smooth and continuous. Being continuous, you can't get from down here to up there without crossing 0 somewhere. So you have at least 1 0. You knew that already. And this tells you you have either 3 or 1 positive real zeros. We looked at it and found out 1 was 1. Did the graph and see, whoops, that's the only one. Okay? The other 2 have to be complex. So we're not going to worry about it. Now, you could do it. You know how to do it. Okay. Now, that was example 9. By the way, there's a checkpoint there. Well worth your time to do it. Another test for zeros of a polynomial function, I think I've already hinted at this one before, is related to the sign pattern in that last row of your synthetic division. That's going to be your quotient, remember? That last row tells you your quotient. This test can give you an upper and a lower bound for the real zeros of F. A real number C is an upper bound for the real zeros of F when no zeros are greater than C. That's called an upper bound. Similarly, C is a lower bound when no real zeros of F are less than C. Okay? That's what the upper and lower bounds are. Well, let's see what that means. Here are your upper and lower bound rules. If f of x is that polynomial function with real coefficients, just like the Descartes rule of signs, okay, and a positive leading coefficient. Now we're requiring that a sub n to be positive. Remember, before we said it just can't be 0. Now we require it to be positive. Suppose the f of x is divided by x minus c using synthetic division, which is usually what we do. We find the rational zeros and then we start using synthetic division. If that c is a positive number, and we usually start with that too, right? Positive number, and then when we do that, and that last row, your quotient down there is either positive or 0. Every number in that bottom row is either positive or 0, then c is an upper bound. Okay? Now, if that remainder was 0, it is the upper bound. Okay, you can't go any higher. If that last one is not a 0, then c is still the upper bound. Don't look at any greater. So again, remember you had all those plus minus, plus minus, plus minus, for your rational zeros. Once you find one of those positive numbers, and then your bottom row is either all positives or zeros, stop. Don't do any more positives. You know you can't find any beyond that. However, if that c is negative, less than 0, a negative number that you're doing synthetic division with, and the numbers in that last row alternately become positive or negative. Zeros count either as positive or negative. So if they alternate signs, with 0 could count either as positive or negative, then c is a lower bound. Stop right there. You can't go any lower. Okay? If you have some lower ones still that you haven't tried, try those. I mean, higher than that lower bound, try those. Okay? I think an example will work well here, don't you think? Okay, let's see one. And they skip them. Shame on them. Okay? Okay, let's do it here. Here's example 10. Find all the real zeros of this function. F of x is equal to 6x cubed. Hey, we've seen this before. No, we haven't. Minus 4x squared plus 3x minus 2. Okay? Before we begin, let's review. What can you tell me about this function in behavior? Say again. Very negative x's are going to be down. Very positive x's up. Because it's an odd exponent, that means they're going in opposite direction, positive coefficient. Okay? So that means it's going like this. What does that tell you right now about zeros? It's got at least one. Because it goes from negative infinity to positive infinity. Got to cross that somewhere. Okay. Now, what's the next thing we might try? Do what? Do what? Descartes' rule of signs? Okay, let's do it. What does that tell us? Say again? Three or one. Positive real zeros. Okay, he's already jumped ahead. Because what do we consider to determine that? Now for negative x, and what does that give us? Negative 6x cubed minus 4x squared minus 3x minus 2. So it has 0 negative real zeros. All right. So we don't have to try any negative real zeros. Good choice to do that next. Then what might we try? Rational zeros test. And what would you put there? Second, the P over Q, where the P's are of the constant term, which would be 1 or 2. See, we don't have to do plus or minuses anymore because you know no negative real zeros. So forget about the minuses on this one. And how about the denominator, the Q? 1, 2, 3, and 6. So what are your possible rational zeros? One, 2. I like to do the integers first. The book doesn't, but. And then what would be your others? That's over 1. Then do them over 2. 1 over 2 would be 1/2, 1/3, 1/6. Did he get them all? Okay, I know he got the ones right. 1/2, 1/3, and 1/6. 2 over 1 we already have. 2 over 2 we already have. Oops, there's another one. 2/3. Yes, because the next one would be 2/6, which is 1/3. So those are the only ones we have to try, right? Don't try any negatives. You know from the rule of sign there's no negative real zeros, okay? And what's the easiest one of these to try? 1. Okay, now don't let this one confuse you now. You used it to find your negative real zeros. You're not going to use it anymore. But what do we write down for the 1? Okay, you do, yeah, but don't do that until you look at these. 6. No, you're not missing any terms. Okay. 6, -4, +3, and -2. Okay. I'll just add those together. What do you get? 9 minus 6 is 3. Yeah. 1 is not going to be 1, so you don't even have to do 1, right? And since we don't have to do the negative, don't do -1, okay? See what it saved us already? What do you want to try next? 2, why not? Let's try 2. Skip a line, draw a line, bring down the 6. You tell me what to write. 12, 8, 16, 19. It doesn't work, but tell me what it is. This time we do go further. 38 and 36. What does that tell you? 2 is an upper bound. Well, guess what? We do that already because that's the biggest one out there. Okay. So, yeah, 2 is an upper bound. It's not a 0, and it's an upper bound. But you see, we got 4 more that are less than 2. You know 1 doesn't work. We've already tried it. 2 doesn't work, so let's start with our good old fractions. We love our fractions, don't we? Yes. Okay. Okay. Which one you want to try first? 1/2. Okay. You start me going here. 3, -1. -1/2. That makes 3 6/2, right? 3 is 6/2. Okay, 6/2 minus 1/2 is 5/2. And, okay. You know it's not going to work. Okay, right? And you know that you have a change of signs. So 1/2 is not enough to round. Okay. So let's just stop there. We know it's not going to work because it's going to be 5/4, and that's not going to add to be 0. Okay. So 1/2 is out. 1's out. 2's out. 1/2's out. Okay. Next. Whoops. What you want to try next? You choose. 1/3. Let's try 1/3. Okay. What would this give you? 2. -2. -2/3. I'm not liking it too much, are you? Okay, that would be 9/3 minus 2/3 is what? Yep. 7/3, is that what you said? Okay, 7/3. It's not going to work, but again, you don't have all positives down there. So 1/3, well, guess what? We knew that. If 1/2 wasn't an upper bound, 1/3 is less than 1/2, so that's not an upper bound either. Okay, so that didn't work. This sounds almost frustrating, doesn't it? Okay, what do we try next? Let's try, oh, he's jumping on to 2/3. Okay, we'll try 2/3. Don't forget, okay, let me go on and cross out my 1/3, just so we don't forget we've already done that. We're going to try 2/3 next. Oh, I erased my 6, shouldn't have done that. What does this give you? Yes, that's a 4, so this gives us a 0, 0, 3, 2, 0. Now, that tells us two things. What are those two things? 2/3 is a 0, okay? So x equal 2/3 is a 0. And I see what the question was. Find all the real zeros. So x equal 2/3 is a 0, okay? All right. That also I don't slash zeros, O's. That also tells me that x minus 2/3 is a factor. Okay, they didn't ask for that, but it tells us that. Okay, now something else this tells us. Look down here. You don't see any negatives, do you? So 2/3 is also an upper bound. Well, doesn't really help us a lot, except that 1/6 may still be 1, but we're not even going to mess with that. Why? You got 3 terms here. What do those stand for? 6x squared plus 3 equals 0. That tell us anything? You say that again? Okay, let's factor it. How would you factor that? Okay, pull out a 3. That leaves you with 2x squared plus 1 equals 0. Now, can 3 ever be 0? No. So let's just wipe that one out. Divide both sides by 3. That would be fine. That leaves us with 2x squared plus 1 equals 0. Now what? Okay, we'll subtract 1 from both sides. If I can't drop my pen. That gives us 2x squared is equal to -1, because that adds a 0. Ah, no way around getting an imaginary number. No matter what x you put in here, when you square it, it becomes positive, if it's a real x, and then multiply it by +2, it stays positive, it can't ever be -1. So that means your other two are complex zeros. And what did it tell us? Either 3 or 1 real zeros. You found your 1, the other two are complex. Okay? And what this says is find all the real zeros. We found 1 and only 1. Okay. Make sense? Okay. All right. Oh, they actually did the 1, didn't they? Shame on me, I didn't do it. I skipped it because I knew it wasn't a 0. If we had done it, we would have seen it was an upper bound. That would have meant we didn't even have to look at 2. But doing by 1 or doing by 2, either one of them would have given us the same information. They have another checkpoint here. I'd highly recommend you try that. And by the way, since we found there are no more real zeros, now our complete factorization using linears and quadratics would be what? complete factorization would have been this first thing, 6x cubed minus 4x squared plus 3x minus 2 can be factored. We already got one factor, right? X minus 2/3. And what's your other factor? 6x squared plus 3. Now, you can do this. I'm not saying that you have to, but you could do it this way. X minus 2/3 times 3 times 2x squared plus 1, right? We saw that was a factorization. We can take this 3 and multiply it by here, and that would give you 3x minus 2 times 2x squared plus 1. And what's that? Yeah, that would be the most direct. And here we have Brianna here. All right. And she made it in before the bell. So, good to go. Okay. All right. We just finished example 10 on page 162 in section 2.5. Now, they left it in that form. They didn't even ask us to do it, but they left it in that form. I'm just showing you a little bit simpler form to do. If you can factor out the 3 like we saw we did, then multiply it by the first factor. That happens to get rid of your denominator there. So now you have no fraction in the denominator. And still, this gives you a 0, x equals 2/3, right? So that works fine. And you can't still can't factor the other one. So to me, that is a simpler form. Okay. Any questions on that? Again, there is a checkpoint, so please do that as soon as you can. All right. Ready for applications? Well, we'll get through this. Remember, we had to. There we go. Application. You're designing candle making kits. That's your first job out of graduation from college, designing candle making kits. Oh, yay. Each kit contains 25 cubic inches of candle wax and a mold for making pyramid-shaped candles. Okay? You want the height of the candle to be 2 inches less than the length of each side of the candle. You want a really squatty, fat candle, right? Okay? Less than the length of each side of the candle's square base. They tell you the base is square. What should the dimensions of your candle mold be? And guess what? You want to use all the candle wax. You don't want to have any wasted. What's that? Okay, yeah. It's a good idea to read it maybe several times so you make sure. Well, what's one of the first things you probably should do on this one? Yes, draw you a picture. Now, even if you draw as poorly as I do, still a good idea to do. So it tells you you have a square base. So I'm going to hope this looks somewhat square. It may not, but pretend it's square. Okay? Now, it's a square base, meaning each side here has the same length. That's really pretty poor. Let me. Ooh, that's even worse. Okay. I'm going to try to do a couple things here. Draw that a little more so it looks like a square. Does that look a little more like a square? Just a tad more, maybe? It still doesn't look very square, but sort of squarish. Okay? Now, a pyramid, and let's name those sides. Okay? Name that tune in. Okay. Name that side. A. Okay? And if it's a square base, that means every one of those sides is an A, right? All right. Now, next thing it says, you want the height of the candle to be 2 inches less than the length of each side of the square base. So the height is pretty short. I'm going to go from the center here and just go up a little bit. So it's going like this, 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 and that. That's going to be your ugly looking pyramidal candle. There's the wick standing right there. Okay? And this is the height. The distance from here to there is your height. What does it tell you here? Very good. H is equal to A minus 2. You see, he translated this sentence right here. You want the height H of the candle to be is equal 2 inches less than the length of the side. We already said the length of the side is A, and you want this to be 2 less than that, so you do A minus 2. That's it exactly. Okay, very good. What should the dimensions of your candle mold be? Well, if we can figure out the A, then we can figure out the H, right? Have we used everything they gave us? Oh, that 25 cubic inches is your volume. Cubic inches measures volume. So we need to know what the volume of a pyramid is. Does anyone know? Okay, you're getting close. Back inside cover of your book. Comes in really handy, doesn't it? And as I think you were saying, it has to do with the area of the base. So I'm going to put A so you don't confuse it with the little a's. The area of the base times the height, except this is a pyramid. If that was a cube or rectangular parallelepiped or something like that, that would be exactly it. But since this is a pyramid and it's got some missing, believe it or not, that's a third of this. 1/3 of the area of the base times the height. That's the volume of a pyramid. If you... No, it doesn't matter what. It could be an irregular triangle pyramid or a hexagonal pyramid. You know, it's the area of the base times the height. Now, unfortunately, the back of the book doesn't have a pyramid. Shame on them. But it's a lot like a cone, right? Circular cone, or any cone, is 1/3 the area of the base times the height. Okay? So it's a pyramid. They don't show this here, but that's what it is. Not fair, but they did it. Okay, so here we have that. So what is the area of the base? We need to get that next. What is the area of the base? A squared. So the volume is 1/3 A squared H. But we know H in terms of A. So we'll do that as 1/3 A squared times A minus 2. And what does that volume need to be? 25 cubic inches. I'll leave off the units for now, okay? But each length has to be an inch and the height has to be in inches. Okay, now guess what I'm not going to do? I'm not going to multiply A squared times that because I want it factored, okay? So I'm not going to do something and have to undo it. But what I will do is try to get rid of that 1/3. How could we do that? Divide by 1/3, which is the same as multiplying by 3. Because now that goes away. Yay. So this gives us A squared times A minus 2 is equal to 75. Okay? You know what? I'm going to have to, I thought I wasn't, I'm going to have to do it. So that's going to be A cubed minus 2A squared is equal to 75. Do y'all want it in that form? How do I want it? Well, where are we going with it? Second, we're going to solve for A ultimately if we can, but you know, frankly, I can't see an easy way to do that. But what are we looking for? Look at the title of this section. Zeros. And to get a 0, what we need to have it equal to? 0. So we need to pull the 75 to the other side. Okay? So now we have a cubed minus 2a squared minus 75 is equal to 0. Okay. Now we have a polynomial equation, and we want to find the zeros. And guess how many zeros we're really interested in? 1. If it came up with a couple of them or 3 of them, that would be interesting. 3 different ways you could design that candle. My gut feeling, there's only 1. But guess what? Are you going to have at least one real solution to this? Yes, you are, because that's the cubic function. Remember your end behavior. You got to have at least one. And I'm guessing that's the one we're looking for. Okay?
You use the h equals a minus 2 as a factor for synthetic division.
Say that one more time.
Where the h equals a minus 2, would you be able to use that as a factor for synthetic division?
A minus, no. I don't think so, because you got to treat the whole problem here. If you could factor by grouping, which it sounds like what you're trying to do, but you can't, because this has an odd number of terms. Factor by grouping, you have to have an even number of terms. And you can't really separate this from that. You have this from this, because this is tied to this, not to that. Is that what you're asking? Okay, so what might we try? To find those zeros. Say again? Descartes' rule of signs. And what does that tell you? Okay, you know you got it. You could have up to 3 real zeros. Okay, we know we got at least one, but what does Descartes' rule of signs tell you? I think you just said it. What do you say? One variation here, so you have one positive. Look at that. One positive real zero. Guess what? That's the only one I'm looking for. Because even though you might have some negative real zeros, guess what? I can't build a candle that has a negative length.
You wouldn't have negative if you would do the f of negative a, you would end up with negative a cubed minus.
Okay, so it does have zero real zeros. Zero negative real zeros. So yeah, if you did the other part of it, you'd find that. But guess what? Since this is a real life problem, and you have to have a candle with a length, and that's what A is. Can you draw me? Yeah, a candle. Make a candle with a negative length. I want to see it. Okay. I want to burn that candle. Okay. I can't. Okay. So we're looking for that one real zero. Okay. So where do we go next? Okay, let's do our rational zeros test. P over Q, and what would that be in this case? 1. Say again? 3. 5. 15. Excellent. 25. 75. And what are our denominators? 1. Okay, we don't even need that at all, do we? And I want that 1 to be it, but guess what? Not going to work, is it? Let's write down our coefficients. What are they? 1, negative 2, 0, good, negative 75. I can add those together, and there's no way that's going to come up being 0. So forget about 1. So what might we try next? Say again? He wants to jump to 5. He is a hard worker, isn't he? But we'll do it. Okay, did he look in? No, he doesn't have a book. I don't know. Bring down the 1. What do you get? 5, 3, 15, 15. Look at him. Okay. He got it on first try, okay? And you also see, don't try anymore, because you know there's only one anyway, but the upper bound test tells you that don't look any further either. That's it. A is equal to 1. I mean 5. A is equal to 5. So it's 5 square inches here, okay? And what then is your height? 3, because it's 2 less. H is equal to 5 minus 2, which is 3. Let's see if that works. 5 squared is 25. 1/3 of 25 times 3. The 3's cancel out. 25 square inches. Yeah, or cubic inches. That works. Make sense? All right. And by the way, there is a checkpoint here. Definitely, it says rework that example when it contains 147 cubic inches of wax candle. That was fun. Okay. Don't think we're going to have time for our vocabulary, are we? You want to start with that next time, or you just do the vocabulary at home? Start with it next time, okay? Homework exercises here then would include any of the odds 9 through 13, either 15 or 17, or both. Any of the odds 19 through 27, either 29 or 31, or both. Either 33 or 35, or both. Either 37 or 39, or both. 41 or 43, or both. Any of the odds, well, you don't have to do if you don't want to, 45 to 49, because those have eyes in them. But if you want to do them, you could. They're fun. Okay. Then do either 51 or 53. They give you some hints. Any of the odds 55, well, wait. All these have at least one 0 that's complex, imaginary part. So you can do those if you want to. They are sort of easy because you already know what the second one is, and then you can go from there. So you can do that if you choose. But definitely do any of the odds 63 through 79, and do any of the odds 81 through 85, any of the odds, this is where we started today, 87 to 93, do either 95 or 97, or both, do either 99 or 101, or both, 103 or 105, or both, 107 or 109, or both. And then for your applications, any of the odds 111 through 113. Okay, either 111 or 113, or both. You get to choose. Then look at the exploration. There's a true-false there. I would definitely go through that. Think about 117. That's 115. Think about 117 through 121, you know, if you want to. You don't have to if you don't want to. 123. 125, I think it has a complex part, so you don't have to worry about that. But you could look at 127 or 129. Well, 129 is complex too, so forget about that. Or you could look at 131. All right. So next time we'll start with our vocabulary for 2.5, and then we'll move into 2.6, which will be the last section we cover before the next test. So what does that mean? Tuesday, no class, remember? No, I'm sorry. Tuesday, there is a class. Thursday, there's no class. So Tuesday, we will do this. I doubt if we'll finish 2.6. So it'll probably be the following Tuesday we finish 2.6. The following Thursday, we'll probably have the test. That's what I'm guessing.
You got to leave
right after class on Tuesday. You will, no, at 9:14. Okay. All right. Good deal.